Now we come to some buzzwords in instrumentation. Now these are some of them, and all of you are familiar with only. I think we'll just go through them. One thing is portable or clamp-on instruments that have come. Then intelligent instruments, Fieldbus, smart transmitters, virtual instruments, telemedicine, MEMS and nanotechnology, wireless integrated network sensors and intelligent control. These are some of the things which are happening in instrumentation. So let us just go one by one to them. About portable and clamp-on instruments, all of you know that nowadays even CROs, you can easily carry them anywhere. Even your these projectors, like this is your LCD projector. Now you can put, such small ones have come, you can put in your that bag in which you are taking your laptop, and you can take it anywhere. So it's always like you like to have portable kind of things, easy to carry. Then clamp-on means you are not going to put any brake and just clamp the thing and you will get the reading. So they are becoming very attractive. So portable instruments are one that can be carried with ease, permitting easy installation and removal. And in commercially, you have got these kind of meters are available: AC/DC current meters, digital multimeters, digital sound meters, power quality meters, laser and photo tachometers. Like this, you know that one is a conventional your tachometer, in which you have to insert it. You have to touch the shaft. Simple tachometer, but this is a digital tachometer, the one which is being shown. The other one is what? A beam is coming, the red beam that is coming. So there must be some here, some black strip or white strip. So the light goes, then it gets reflected, then you count how many times in 1 second, how many you got. So this is a non-contact kind of device. Then these are the sound meters, the digital sound meters which are there. Then multimeters, such compact, otherwise you think of those analog meters, how bulky they were, and then because they are so much mechanical movement is there, so friction is there, wear is there, hysteresis is there. Now they are all made around a single ICs only, so they are very light also, very accurate also. Then you have power quality meters. These tongue-on type, they are clamp-on. Like this your AC/DC current clamp meter. Mostly they are working on Hall effect transducers. Simply a wire is going, you simply clamp it, you get the reading. Then the next comes integrated, intelligent or smart sensors. Sometimes they are also called SMTs also, like silicon micro transducers. The same technology that is used for IC fabrication, that is used for making sensors also. So you integrate the signal processing also with the sensors. You don't attach externally, like normally what we do is we put a sensor, then that sensor output we take to signal conditioning circuits, then finally display or control. But if on the same chip you have sensing as well as signal conditioning, so it will naturally give a better quality of measurement. You can design it to remove interfering signals also, temperature compensations, offset, non-linearities. These things you can remove by that signal conditioning circuits. So a smart sensor will, smart normally we say anything smart, we say it has microprocessor, some intelligence in it, isn't it? So a smart unit will include automatic calibration, interfering signal reductions, interfering and modifying signals which affect the signal, so their reduction will be there, offset correction will be there, and another thing is very important, self-test. They will themselves testing and calibration, self-calibrations will be taken in that unit. So the characteristic of smart sensors are better signal to noise ratio, on-chip feedback systems or lookup tables are there which will improve the linearity of the system. Suppose it is inherently giving you non-linear, so it will give you linearized output. Then compensation circuits are there. You have cross sensitivity, like you want it to be sensitive only to desired input, but it is also sensitive to interfering and modifying inputs. Like you want to measure strain, it is also sensitive to temperature. It is also sensitive to 60 hertz noise that is present there. So those cross sensitivities that it has, so that also it will compensate for. And you will also have on chip, you will have current sources and voltage sources, which will act as, which will help for calibration purpose. So you can calibrate your instrument with help of them. Then the next is a Fieldbus. This Foundation Fieldbus is an organization which sets standards for them. initially we had actually heart protocols, and heart was something that in which analog was also there and digital was riding over the analog signal. But now we have Fieldbus Foundation, which is totally digital communication. It's 100% digital, and it has replaced the 4 to 20 milliampere analog signal. All of you know that in industry the standard is 4 to 20 milliampere signals, and it is based on your OSI model, that 7 layers that you have of communication. So on that model it is based upon. And the predecessor, now also there are HART protocol is being used, it is, but this HART stands for Highway Addressable Remote Transducer Protocol. So this was an early implementation of Fieldbus, which is a digital industrial automation protocol. It's total digital, while HART was both analog plus digital. Already the 4 to 20 milliampere will go, but on that you will be putting digital also. So in HART, the technique that was used was frequency shift keying concept. You will represent your analog signal by ones and zeros. So 1 will correspond to certain frequency, 0 will correspond to certain frequency. That was the HART protocol. And HART protocol, it was developed by Rosemount. As you know, Rosemount is a company which has taken initiative in many things like making your first PLCs, DCAs. They are leaders in instrumentation. Honeywell, Rosemount, Yokogawa, they are the leaders. So HART protocol was developed by Rosemount, and it was built on Bell 202 standard, which uses frequency shift keying. So what they do is that 1, like you have converted an analog signal to a digital signal. So 1 you represent by 1200 hertz signal, and 0 you represent by 2200 hertz signal. That's what the thing is. And it's a two-way communication. So you will use that existing 4 to 20 milliampere lines only for like you are giving the command, you are asking the instrument, give me the reading. Then you are asking the instrument something, that is a command. Then the instrument when gives a reading, then that's a response from the instrument. So command signals, response signal, they are getting two-way, both communication is there. And the baud rate is 1200 baud for HART, the rate at which how many bits per second. So this is the kind of thing that you have an analog signal and superimposed upon you have a digital signal. So it doesn't affect, because it's a frequency signal, so average value is 0 only. So it doesn't affect your analog signal also. The analog value is not affected, it is overriding on that. Then this is, you can see a control valve is there. In this there is a round card has been shown. This is a round card has been shown. And what does it contain? You can mount it on this control valve. It contains modem. You can communicate. It contains a processor. It contains memory, RAM, EEPROM, and all the logic and software necessary to execute the HART protocol. It's a small simple thing you attach on the wall. It can be connected to your HART bus also, and very intelligent transmitter it becomes. So Fieldbus is a digital bidirectional serial bus communication network linking isolated field devices such as controllers, transducers, actuators and sensor, and each device is able to execute simple functions such as diagnostic, control, maintenance functions, as well as provide bidirectional communication capabilities. This is what the Fieldbus is. Now you can see, like, this is the Fieldbus. You have data acquisition control systems, you have so many other intelligent transmitters, devices are there. This is a human machine interface, all connected to this Fieldbus. But then all these equipment, they have to be Fieldbus compatible also, that is there. Then you have, in larger perspective, you see, if you have sensors, actuator bus is different, then this is a field level, this is a process level, this is a SCADA level, and this is your field bus. These are PLCs. So these are your direct IOs, they are going to PLCs, also connected to field buses. So this is that planning. In plant hierarchy, you can see field bus. Then comes smart transmitters, because smart transmitter will be like, it will either be following that HART protocol so that it can be connected to other parts, isn't it? So smart transmitter, in fact anything smart means it has some intelligence in it. Nowadays you have smart washing machines also, isn't it? So what are those smart washing machines? They have microprocessors in them. They have fuzzy machines also, isn't it?
Refrigerators also.
Refrigerators also, that's right. In fact coolers also, we are saying they are also smart. So Smart means wherever the intelligence has been built into there. So smart describes any device based on microprocessor, microcontroller, which provides intelligence, control and data storage. So because when you keep microprocessor, you are having functionalities like multiple sensor types. In that smart transmitter, like you have connected now RTD. Afterwards you can connect thermocouple also. Thermocouple also of any type you can connect. Now you have connected K type, then afterwards connect J type, connect R type, S type. So you can have multiple kind of instruments into that. Then multiple measurement variables also. You have smart pressure transducer, it also gives you temperature values also. It gives you volume flow rate also. The same transmitter can be used for more than one measurements. Then temperature compensation is provided. The outputs could be many, you can specify it in milliamperes, in volts or in 4 to 20 milliamperes. You can specify the units also, pressure, I want in inches of water, I want inches in mercury, you want millimeter of mercury, you want centimeter of mercury, you want meter of water. Whatever unit you specify, it will give into that. So this is a simple like block diagram. You have sensor which contains strain gauges, RTDs, thermocouple, resistive transducers, flow transducers, all converted, all the transmitters, they will finally will be reduced to a signal of 4 to 20 milliamperes. So they will be given to ADC, there will be a 24 volt supply, then a resistance will be there. So all the signals will be converted into 0 to 5 volt range. So you can then interface to ADC, and then isolation barriers are provided, then you have microprocessor memories, then you finally give to DAC, then which again converts it back to 4 to 20 milliampere for controlling signals. This is our measurement, then the controlling part comes. Or see, this is a simple which is not smart transmitter, simple sensor, transmitter, then controller. Now here is a smart transmitter which has sensor, A to D converter, microprocessors, memory, then D to A converter 4 to 20 milliampere, then again it communicates it back here also. So like you have SFCs also, smart field communicators also, which will communicate with the transmitters. So small handheld kind of things, you can communicate, you can give the commands, you can receive from there. Features of transmitters are configurations, you can configure them to various kind of transducers, you can rearrange the sensors that now I want from this range to this range on this units you want. So you have a smart field communicator, through that you can do it. Then you have signal conditioning circuits, like noise can be totally eliminated. So that is there also inbuilt. Then self diagnostics, it will itself diagnose itself, tell that if there is a failure, what is the cause of failure, it will test itself periodically only. So you have like from Omega Engineers, you have this PX series. It is a both temperature and pressure transducers. G stands for gauge. This is a high temperature plus differential pressure transmitter, and you can see the cost also, like if you compare the cost also, because here it is high temperature and differential pressure, so the cost also is more, and they are made from you can get them from Omega Engineers. And of course then very famous ones are these Rose mounts, where CA stands for commercial grade absolute pressure, A will for absolute, G for gauge pressure, D for differential pressure. So this is how it will be. Then Rose mount series is there, 1151, which came in 1969, that long back. That was the first smart pressure transmitter which came. And then 3051 is there. It has also compatibility with Field Foundation bus, this transmitter. Then Rose mount 3144 is there, which is a temperature transmitter. Then comes MEMS and nanotechnology. All of you know the full form for MEM is micro electromechanical systems. So as the name says, they are at micrometer scales, and nanotechnology is at nanoscale. The importance of this is that you are using your IC fabrication techniques to make mechanical systems also, like cantilevers you can make, diaphragms you are making, then valves you can make, motors you can make, pumps you can make, gears you can make. Like IC fabrication comes under microelectronics area, but under MEMS and that is a two-dimensional. You are making two-dimensional structures in microelectronics, but in MEMS you are making three-dimensional structures. And the techniques are also somewhat different, like Lija techniques, and they are used for MEMS fabrications. So you can have like monolithic integration here, where MEMS device and integrated circuit are on the same piece of silicon. And you can have system in a package kind, where MEMS device, they are in the same package, not on the same chip, but they are in the, like there is a sensor circuitry and there is a signal conditioning circuitry, but not on the same substrate. So that's a system on a chip. And these are the components of MEMS: microsensors, microactuators, microelectronics, and microstructures. So you have MEMS based sensors are there, MEMS based actuators are there, then MEMS based systems are there, and microelectronics is a part, because fabrication part that is dictated by microelectronics. So the core elements are sensing and actuation, and then you have a signal transduction unit, that is signal conditioning unit. The first major commercial MEMS sensor was accelerometer, and this is used in your airbags, which are used in automotive vehicles. Whenever a collision comes, accident is there, so there will be an airbag which will get inflated. So you will not get that impact, no? Otherwise, most of the time on steering wheel you get the impact, or the passengers or the which are sitting in the rear wheel, they also get that impact, they hit the seat. So this is how it looks like. You have a sensor here. So when the impact, the collision is sensed, then what it does is, this releases this nitrogen gas, so this airbags get inflated, and then it comes in front of you, it saves you. This is the first commercial application of MEMS based sensor. Then you also have gyroscope also, which are also MEMS based. This is, can you identify what is this? This is, what is this MEMS based? What are we trying to realize here?
The valves.
Yes, for sure. What kind of valve it is? They are studying valves? No, okay. You know about check valves?
Yeah.
What are check valves? They allow only flow in one direction. Like in our heart also we have check valves. Impure blood should not go back to the heart, isn't it? So there it's only so here also you can see, when the flow is in this direction, what it will do? It will close it only. Only when it goes in this direction, then only the valve will get open. So these you can realize in MEMS. So these kind of valves are coming in MEMS. Check valves they are called. Now this inkjet printer heads, there also you are using MEMS. Those piezoelectric actuators are there, so they will do it. Then automobile airbag sensors I have told you. Then optical MEMS is again a very big field, and the very important one is bio-MEMS, which are coming for drug delivery, drug designing, for medical aids. They are coming in big way. So commercial applications you have, and then automotive applications are there, and then you have in bio-MEMS, that is one area. Then about virtual instrumentation. As the name says, it's a virtual instrument. You are not handling actually the instrument, but all the functionalities you are able to realize it on your PC only, isn't it? And the biggest advantage of virtual is that otherwise you go to buy an instrument, the vendor will give you the specifications, you will see which one fits you best, and maybe like you are getting say even 50 megahertz CRO or 1 gigahertz CRO also, but you may not be using all its capabilities. But using virtual instrument, you can have a user defined instrument, the way how much range you want, which parameters to measure. So you will make your instrument according to your needs. The vendor will not dictate. That's a user defined instrument, and again it is using the technology of what? PC, because that display is there of PC. So that display of PC can be used as it can look like an instrument only. Then you have data acquisition devices to interface from the real world, you take the signals. Then you have some program like LabVIEW is there, Daisy Lab is there. So then you can write a program, you can make a virtual instrument. I don't know how many of you are reading at least this Hindu. If you read on every Thursday, there is a science section and you get very good articles. I remember I must have read about virtual instrument 10 years back. It came in Hindu only. Now also a few days back only on Hindu it came smart dust, that is these wireless sensor networks. Then only 2 days before it came that you have now bio batteries are coming, which are using glucose and sugar, and 50 milliwatts you can get from them. So I recommend that you should take Hindu and read its science section. Every day also some news come, but science section is really good. So there I read the first thing that you can make your CRO using PC only. Your PC can act as a CRO. You need not go and buy a CRO. So that is the concept. So the basic thing in virtual instrumentation is that you are creating user defined instruments. That is the most important thing, which will include modular hardware will be there, like sensors will be connected to the PCs through your data acquisition boards. Then development software will be there, like as I told you, LabVIEW is there for National Instruments. Then PC technologies, that all you are using, display technologies. So virtual instrument can be defined as a software centered system that exploit the computing power, productivity, display and connectivity capability of computers. See, you have net on your computers, so you can send your whatever reading you have taken, you can send it across the world anywhere. Right? That is why the concept of remote lab has come. There is a lab in your department, there is a lab, but anywhere from across the world anybody can access your lab. That's the concept of remote labs. So it's a software centered system that exploits computing power, productivity, display and connectivity capability of computers. So engineers and scientists, they build measurement and automation system that suit their needs exactly, instead of being limited by traditional fixed function instruments which are vendor defined. So virtual instrumentation solutions, they will result in lower capital cost. You already have a PC, you are using your PC for many purposes, so it's a lower cost only. Then lower system development cost also. Then lower system maintenance cost also, and less time to market also. And see, when you are making an instrument, you will be making certain modules. Now that same module you can reuse in any other kind of instrument also. It is just like you write a subroutine. That subroutine you can use it. You have written a subroutine, say for some taking exponential something, so you can use it anywhere you need it. So here also you have made a VI, and that VI file you can use it as a sub VI, you can use it anywhere. So that is. So what is a virtual instrument will contain? It will consist of an industry standard computer or workstation equipped with powerful application software, then cost effective hardware such as plug-in boards and the driver software. These are the three things that you need to make a virtual instrument. LabVIEW is the most popular one, like 80% of the virtual instrumentation that is being handled by LabVIEW only, which is if you see ni.com, you should go and always visit ni.com. That will give you what are the latest software they are releasing, what hardware they are coming with. That is a leading company for this LabVIEW. So this is a software for virtual instrumentation. It provides so many data acquisition cards. It has motion, image, those cards are also there. Then SCXI cards are there, which are made for industry standards only. Then simple data acquisition card for your experimentation lab purposes also. Then you have, it uses graphical programming. Otherwise you are writing programs in C, that's a textual programming. But here what you are using is, you have icons are there. You simply connect them together. You wire them together. So it is a graphical programming. I hope you are using LabVIEW. Yes. Most of you are using LabVIEW, that's good. Then data storage and analysis for a wide range of applications. So all of you know that, I think I should not spend more time on that. Then this is like a front panel which will act like an instrument. This will seem like an instrument, and it will contain inputs which are control inputs and indicators which are outputs. And how the inputs will be converted into outputs, so you will write a program. That what you are acting upon them and what output you want, that you will do. So you have a front panel which is a user interface, controls as inputs, indicators as outputs. Then the block diagram is a graphical code. So data travels on wire from controls through functions to indicators. So this is how, like it is something like you write a flow chart, how the data is flowing. So that is in the block diagram. The program part is in block diagram, and front panel is this. So front panel will serve as the user interface. Block diagram contains the graphical source code that defines the functionality of the VI. Now if you take a simple example, like you have a level sensor, and then this level sensor, the output will be 4 to 20 milliampere. So you have standard 24 volt supply. You drop it through a resistance, say which is of 249 ohm. So 4 to 24 milliampere will correspond to the lower part of the range, and 20 milliampere to the upper range. So that will get converted to voltage of 0.996 to 4.98, which you can directly feed to DAQ devices. So, if I draw this diagram for this, which will show level versus current, so then you can say that you can write a relationship, it is a linear curve. So, when it is 4 milliampere, the level is 0, and when it is 20 milliampere, the level is 50 feet, isn't it? So, now you can write an equation which relates L to I. And so, you get an equation, simply L is 25 by 8 I minus 25 by 2, isn't it? And then this I you can convert, because resistance is there known to us, that is 249 kilo. So, you can just write this value. Now, you can realize it, because V you will be getting from the level sensor through, when you are dropping through resistance, you are getting the V. So, you take to your LabVIEW program this V multiplied by 25 divided by 8 into 0.249 minus again divide by minus subtract 12.5, you will get your reading, directly you will get the level reading. So, this is how you can realize it. So, this is your those modules, which is AI samples channel, then you do all this and you will get your thing. These are simple things just to tell you that you can use virtual instrument like this. Then comes telemedicine. Now, telemedicine is investigation, monitoring and management of patients. These are the 3 things in telemedicine. You investigate the patient, you monitor the patient and you manage the patient. These are the 3 things. And again, what are the technologies that will be used here? Telemedicine. At afar you are doing it. So, naturally communication technologies come. So, communication technologies plays a very important role in telemedicine. So, and it is very useful, especially for areas where experts, doctors cannot reach. Like in our rural areas, we are always reading that our villages are not getting doctors. As such, we have less doctors per person. If you see, we have very less doctors, and then they are also concentrated in big cities only. They are not in villages. So, villages have to pay a lot for coming to this cities, and then paying also so much. So, telemedicine can help a lot these rural people. And there are 4 components of telemedics. One is a remote database access or update, then telemonitoring, from the distance you monitor, then you can have video conferencing, which is very popular these days, then case handling or message passing. These are the 4 components of telemedicine. You have also heard of this tele surgery also. Surgery is also taking place from a distance only. Or there could be one doctor with the patient, other expert is there. The expert is commanding that you do like this, you do like this, and the operation is going on. Now, there are 2 modes for, like, you have got this data, and the transmission modes, there are 2 modes, real time mode and the store and forward mode. Now, which one do you think is more critical? Real time mode. Real time mode is very critical. At the same time, the decisions have to be taken, the messages have to go, and store and forward is something like BPOs are doing. You can, at that time, they can, all the data can come, you can then process it. You have to keep history of the patients. So, it is coming and you have a file, you keep recording them and then analyzing that, yes, the BP is varying like that, ECG is going like that. So, you can analyze it at your time, whatever is suitable to you. So, real time is more critical. So, here immediate feedback is essential. So, in conferences also you need, you are talking, the other person should reply at that time only. No? So, wherever you have emergency consultation, you need real time transmission. You have interactive treating situations, there also you need real time. Meetings also you need real time mode. While store and forward mode, you do not need immediate feedback. Data is stored, forwarded and assessed at the hub at a scheduled time, at the convenient time. And of course, it is less costly also. And the thing is, you can compress the data and then send it afterwards. And there you have to send it raw as such. So, that way also it is very efficient. Thank you.